Hey guys, welcome back to another video. In today's video, I'm going to be going over some practice problems regarding concavity of functions and the second derivative test. So let's begin. So for our first problem, it's asking us to determine the intervals where f of x is concave upward or concave downward. To determine concavity, we have to take the second derivative of the function. So let's start with the first derivative, which will be equal to 2x minus 4, and then we'll take the second derivative, which would be just 2. So as you can see, for all x, for the second derivative of x, it's just going to be equal to 2, which means that the second derivative is always positive for the whole number line. So from negative infinity to positive infinity, f prime prime of x is positive, which means that it is concave upward for its entire interval, so from negative infinity to infinity. And this can be shown with the graph of the function, as it would look something like this. This should be 0 over here. So as you can see, it's concave up because its entire curve faces up for its entire domain. So now we're going to look for all the points of inflection of f of x is equal to x to the power 4 minus 6x squared plus 2x. So points of inflection occur when the second derivative changes signs from either negative to positive or positive to negative. So now let's find the first derivative, because we have to get the second derivative by differentiating the first derivative. So now we have 4x cubed minus 12x plus 2. Now we differentiate once more. So now we have the second derivative. So now you have 12x squared minus 12. And now we're going to find for values for when the second derivative is equal to 0. So we're going to solve for the values when the second derivative is equal to 0. So what we're going to do here is factor out a 12. So now we have 12c squared minus 1. And this is just difference of squares. So we can just say this is 12c plus 1 and c minus 1. So now we have our possible. So these are not the points of inflection yet, but they are possible points of inflection because we have to verify that the second derivative actually changes signs at these points. So let's say this is negative 1 and this is 1. So now we're going to test values in between these intervals to make sure that the second derivative changes sign. So we're just going to do sign analysis here. So let's plug in negative 2 into the second derivative of x. So now we have 12 times 4 minus 12, and that's 36, which is greater than 0, which means that the second derivative is positive here. And now we're going to do the same thing from the interval negative 1 to 1. So now let's try second derivative of 0. So now you have 12 times 0 minus 12, and that's equal to negative 12, which is less than 0, which means that this interval is negative. And now I'm going to try from 1 to infinity. So I'm going to plug in positive 2. And that's just the same thing as this one up here. So that'll be 48 minus 12, which is 36, which is greater than 0. And we can determine that points of inflection occur at negative 1 and positive 1. But now we're going to find the y value. So we just plug in f of negative 1. F of negative 1 will be equal to 1 minus 6 minus 2. So now we have negative 8 plus 1, which is just negative 7. And now we're going to do the same thing for positive 1. So f of 1 is equal to 1 minus 6 plus 2. And that's 3 minus 6, so that's negative 3. And these are our 2 points of inflection. Okay, so now we're going to determine the intervals where f of x is equal to sine of x is concave up or down, and the points of inflection on the interval 0 to 2 pi. So we're going to take the first derivative of sine x, so now we have cosine x. And we're going to take the derivative of cosine x for the second derivative, so now we have negative sine x. So now we're going to solve for values where the second derivative is equal to 0. So sine of c is equal to 0. So what values of sine from 0 to 2 pi is equal to 0? So of course sine is equal to 0 So this is a unit circle. Imagine this is just a unit circle. So when it's at 0 degrees or 0 radians, sine is equal to 0. And when you're at pi radians, sine is also equal to 0. And when you're at 2 pi radians, sine is also equal to 0. So our possible intervals come from 0, pi, and 2 pi. But since 0 and 2 pi are already on the boundary, we don't have to consider them, so we can just draw the number line like this. So we have the second derivative of x from 0 to 2 pi, and the only thing between them will be pi. And we're going to test values in between these two to see if the function is concave up or down. So let's plug in pi over 2. So at pi over 2, so the second derivative of pi over 2 is equal to negative sine pi over 2, and sine pi over 2 is equal to 1, and negative times positive 1 is just negative 1. So we have that this interval is negative. And now let's test from pi to 2 pi. So I'm going to plug in 3 pi over 2. So f prime prime of 3 pi over 2 is equal to negative 1 multiplied by negative 1. Because sine of 3 pi over 2 is equal to negative 1. But since we have the negative coefficient, we multiply by negative 1. So negative times a negative makes it positive, which means that this is positive. So to answer this question, we're going to find the open intervals, because the intervals where it's concave up or down will be open. Because if you switch from concave down to concave up, or from up to down, there's a point that where it occurs, it switches from. But you can't have both at the same point. So that's why the interval is open. So from 0 to pi, the function is concave down. The function is concave up from the open interval pi to 2 pi. And we have a point of inflection at pi because it switches from negative to positive. So our point of inflection, I'll write down here, will be at pi. So f of pi would be just 0. And that's our answer. Okay, so now this problem is asking us to use the second derivative test to classify the critical points of f of x, where f of x is equal to x to the power 4 minus 4x squared. So the second derivative test is that when the first derivative at c is equal to 0, and if the second derivative at c is greater than 0, then f of c is a relative minimum. And if the second derivative is less than 0, then f of c is a relative maximum. So let's utilize this for this question. So let's take the first derivative. So the first derivative of x is equal to 4x cubed minus 8x. So now let's take the values where the first derivative is equal to 0. So 4c cubed minus 8c. I'm going to factor out a 4c. So now we have 4c multiplied by c squared minus 2. And we have that a c value is equal to 0. And that the other c values are when c squared minus 2 is equal to 0. So c squared minus 2 is equal to 0. So c squared is equal to 2. And we have that c is equal to plus or minus square root of 2. So I'm going to put plus or minus square root of 2 into here. So I'm going to erase everything and put that c is equal to 0 and plus or minus square root of 2. And now we're going to find the second derivative. So we take the first one again, 4x cubed minus 8x. And we take the second derivative based on f prime of x. Now you have 12x squared minus 8. And now we're going to plug in values into the second derivative. So the second derivative of 0 is equal to 12 times 0 minus 8, which is negative 8, which is less than 0, which means that the point 0, f of 0, is a relative maximum. And now let's try the other two values. So the second derivative of the square root of 2 is 12 times 2 minus 8, which is 24 minus 8, which is 16, which is greater than 0. So we have a relative minimum at the point square root of 2, f of square root of 2. And now we're going to find the value of the second derivative at negative square root of 2. So now we have f prime of negative square root of 2. That is be 12 times 2 again, which would be equal to 16, which is greater than 0. So we have two relative minimums at the points square root of 2 and negative square root of 2, f of negative square root of 2. So now we're going to find the f values of these points. So we just plug them back into the original function. So we have a relative maximum at f of 0. So 0 minus 0 is just 0, so this would be 0. And now let's find the value of square root of 2. So f of square root of 2 will be square root of 2 to the power of 4, which will just be 2 squared, which would be 4, minus 4 square root of 2 squared, which is just 2. So now we have 4 minus 8, and that will be negative 4. So we have that this value is equal to negative 4. And since these are even degree values, it's always going to be positive. So this will also be negative 4. So that's the end of this question. So now we're going to explain why the second derivative test fails for the function f of x equal to x cubed. So first let's take the first derivative. And now you have it's equal to 3x squared. And this is equal to 0 when c is equal to 0. So now let's take the second derivative. So f prime of x is equal to 6x. So now let's plug in f prime of 0. Second derivative at 0, which would be 0. But the second derivative test only works if the second derivative at c is greater than 0, or if it's less than 0, which is not the case here because it's equal to 0, which means that we have to use the first derivative test to verify strema. Okay, so now we have this problem, which asks us to find the interval to concavity, points of inflection, and whether the first and second derivative tests can be used to find the extrema of this function. So let's start with the first derivative. So the first derivative is equal to 1 over 3 multiplied by the inside to the power of negative 2 over 3 multiplied by the derivative of the inside by chain rule. And this is going to be equal to 2x over 3 x squared minus 1 raised to the power of 2 over 3. And now we're going to check if the first derivative test can be used to find the extrema. So we're going to look for values when the first derivative is equal to 0 or undefined. So let's start for them. So f prime of c is equal to 0 when the numerator is equal to 0. So we can disregard the denominator for now. And you can see that c is equal to 0. And now let's solve for when f prime of c is equal to undefined, or when the denominator is equal to 0. So let's just say this is 1 over 3 x squared minus 1 2 over 3. Or you can say this is just 2x instead of x is c. So since the numerator and the denominator don't have any common factors, you can just say this is equal to 1 and just solve for when c is equal to 0. So you can see that on the inside we have c squared minus 1. When we set this equal to 0, we can find the values of c such that it is equal to 0. So you see that c squared is equal to 1, and that c is equal to plus or minus 1. So I'm going to rewrite everything here. We have the f prime of x is equal to 2x over 3 x squared minus 1 to the power of 2 over 3, and that c is equal to negative 1, 0, and positive 1. And now we're going to test values around it to make sure that these are possible points of extrema. So let's try negative 10. So f prime of negative 10 will be equal to negative 20 over 2, 100 minus 1, 99, 2 over 3. So this term will be positive, but this upper term will be negative. So which means that this is a negative. So this interval is negative for the first derivative. And now we're going to test from negative 1 to 0. So let's try f prime of 0.5, negative 0.5. So let's see, 2 times negative 0.5 would be 1, 3 multiplied by 0.25 squared, or negative 0.25, well, that would just be 0.025 minus 1, which would be raised to the power of 2, which means that no matter what, it's going to be positive because there's a 2 in the degree, which means this would just be negative 1 over positive, or negative over positive, which would just be negative, which means that this interval is also negative. So now we are going to test from 0 to 1. So now let's try f prime as 0.5. That's going to be equal to 1 over 3, 0.5 squared, which would be 0.25 minus 1. That's going to be negative, but since you're raising it to the power of 2, it's going to become positive. So this is just positive over positive, which means that this is positive. And now let's test from 1 to infinity. So let's plug in 2. So f prime of 2 is going to be equal to 2 times 2, 4 over 3 multiplied by 2 squared, 4 minus 1, which is 3 to the power of 2 over 3. But as you can see here, it's positive over positive, which means that the extrema only occurs at the point 0, and it's going to be a relative minimum. So yes, the first derivative test can be used to find extrema. The relative extrema occurs at 0, f is 0, so we just plug in 0, negative 1 to the power of 1/3, which would just be negative 1, because it's just essentially the cube root of negative 1, and that's still negative 1. So yes, we can find the extrema using the first derivative test, and it will be at 0, negative 1. Okay, so now we're going to find the intervals of concavity. So we're going to take the first derivative and then differentiate it again. So we have 2x over 3, x squared minus 1 to the power of 2 over 3. And now we're going to differentiate that again for the second derivative. So the second derivative, but what I'm going to do here, I'm going to factor out the coefficients and then multiply by the derivative of everything else inside. So now we have d dx of x over x squared minus 1 to the power of 2 over 3. And now I'm going to use quotient rule to simplify. So now we have 2 over 3 multiplied by x squared minus 1 to the power of 2 over 3 multiplied by 1, subtract or minus x multiplied by the derivative of the bottom. So we got 2 over 3 x squared minus 1 to the power of negative 1 over 3 multiplied by 2x all over x squared minus 1 to the power of 4 over 3. Okay, so now I'm going to simplify this a bit more. So we have 2 over 3 multiplied by x squared minus 1 to the power of 2 over 3 minus 4x squared over 3 multiplied by x squared minus 1 to the power of negative 1/3 all over x squared minus 1 to the power of 4 over 3. So what I'm going to do now is multiply both the numerator and the denominator by x squared minus 1 to the power of 1 over 3 to get rid of this term, and then to simplify this term and this term. So now you have that this is equal to 2 over 3 multiplied by x squared minus 1 to the power of 1 minus 4x squared over 3. And then since we're multiplying by x squared minus 1 to the power of 1 over 3, it will cancel out. So it should be 1 all over x squared minus 1 to the power of 5 over 3. So I'm going to erase this, but move this onto the next part. to simplify it even further. Okay, so now let's simplify this. I'm going to multiply both sides by 3 over 3. So 3 and then 3 on the bottom to get rid of this 1/3 fraction over here. So now we have 2/3 multiplied by 3 x squared minus 1 minus 4x squared all over 3 x squared minus 1 to the power of 5 over 3. And now I'm going to simplify this, and then this will turn into 2 over 3 multiplied by 3x squared minus 3 minus 4x squared all over 3x squared minus 1 to the power of 5 over 3. So now this will simplify into 2/3 multiplied by negative x squared minus 3 all over 3x squared minus 1 to the power of 5 over 3. So now I'm finally going to multiply by the coefficients from earlier. So now you have 2x squared minus 3 over 9x squared minus 1 to the power of 5 over 3. This should be 6. I forgot to multiply into 3. So this should be equal to negative 2x squared minus 6 over 9x squared minus 1 all over 5 over 3. And this would be our second derivative. I'm going to erase everything so that it becomes a lot neater, and so that we have more room to do these 3 steps again. Okay, so now we're going to find the intervals of concavity. So to find these intervals, we're going to find when the second derivative at c is equal to 0 or undefined. So to find when it's 0, we're only going to worry about the denominator. So when f prime prime of c is equal to 0, that's when negative 2c squared minus 6 is equal to 0. So I'm going to multiply both sides by negative 2. Divide both sides by negative 2. So now we have 0 is equal to c squared plus 3. And I'm going to subtract 3 from both sides. And now we have that negative 3 is equal to c squared. But the issue here is that this is not going to be a real answer. We're going to have the square root of negative 3, which is not real, which means that there is no second derivative where c is equal to 0. So now let's check for when it's undefined. So we're only going to worry about the denominator. So we're going to solve for when the denominator is equal to 0. So I can divide both sides by 9 and get rid of the degree. So now I have that c squared minus 1 is equal to 0, and that c is equal to positive and negative 1. So now I'm going to use these values to split the interval of the second derivative of x. So f prime prime of x, we have infinity to negative infinity, and from negative 1 to 1. And now we have these 3 intervals. So let's try the second derivative of x at negative 2. So the second derivative of x at negative 2 is going to be negative 2 times 4, negative 8 minus 6 will be negative 14 all over 9 times 4 minus 1, which would be 3 to the power of 5 over 3. So this is positive, but this is a negative over positive, which means that this interval is concave down. And now let's try from negative 1 to 1. So I'm going to plug in the second derivative at 0. So negative 2 times 0 minus 6 would be negative 6. 9 times negative 1 to the power of 5 over 3 would be 9, 0, negative 1, 5 over 3 would just be negative 1. So now we have negative 6 over negative 9, and that will give you positive 2/3. So this whole interval is positive. And now from 1 to infinity, we're going to plug in the second derivative at 2, because that's in between 1 and infinity. So we have negative 2 times 4, negative 8, minus 6, negative 14, over 9 times 4 minus 1, 3 to the power of 5 over 3. So this is positive. So we have a negative over a positive, which is just negative. So now we can find the intervals of concavity. So we know that the function is concave down from negative infinity to negative 1, union 1 to infinity, well, positive infinity, and that is concave up from negative 1 to positive 1. And we can find that there exists points of inflection because the graph, well, the second derivative of x switches from negative to positive at negative 1 and from positive to negative at 1. So we have 2 points of inflection at negative 1, f of negative 1, and at positive 1, f of 1. So I'm going to write this a bit neater. Okay, so now we're going to find the points of inflection by plugging in negative 1 into the original function. So let's plug in negative 1. So f of negative 1 is going to be negative 1 squared, or positive 1 minus 1 to the power of 1/3. So that's just 0 raised to the power of 1/3, or 0. So this point of inflection occurs at negative 1, 0. And the second point of inflection will occur at 1. So f of 1 is 1 squared minus 1 to the power of 1/3, which is 0 to the power of 1/3, which is also 0. So these are the 2 points of inflection, and these are the intervals of concavity for the function. And now we're going to check if the second derivative test can be used to find the extrema of the function. Okay, so we're going to determine whether the second derivative test can be used to find the extrema. So this can be used when the first derivative is equal to 0, and when the second derivative is either positive or negative at that point. So let's solve for values when the first derivative of x is equal to 0. So f prime of c is equal to 0. We're only going to look at the numerator, because if you look at the denominator, we will only find values that make the function undefined. So 0 is equal to 2c, divide both sides by 2, and now we have that 0 is equal to c. And now we're going to plug in 0 into the second derivative. So the second derivative at 0 is going to be equal to negative 2 times 0 minus 6 over 9. 0 squared is 0, so you have negative 1 raised to the power of 5 over 3. So now we have negative 6 over negative 9, and this will simplify to 2 over 3, which is positive, which means that the point 0, 0, f is 0, so let's plug in 0 into here, 0 minus 1 to the power of 1/3 is just negative 1. So we can say that 0, negative 1 is a relative minimum of the function. And this lines up with what we did at the beginning for the first derivative test, which means that yes, both methods can be used to find the extrema for this function. So first, we're going to start with the first derivative. So f prime of x is equal to cosine x minus 1/2 cosine 2x multiplied by 2. And this will give us cosine x minus cosine 2x. So to utilize the second derivative test, we have to find values where the first derivative is equal to 0. So what we can do here is set that f prime of c is equal to 0, and that cosine of c minus cosine 2c is equal to 0. And what we're going to look for now is what value c exists such that cosine of c minus cosine 2c is equal to 0. So like what angle on the unit circle exists such that the cosine of this, when multiplied by 2, will be the opposite of the first one. And when you subtract from each other, will be equal to 0. Or what we can do instead is ask what values of c exist such that cosine of c is equal to cosine of 2c. So the first value that comes to mind is 0, because cosine of 0 is 1 and cosine 2 0 is 1. So, but that's on the boundary, and so is 2 pi. Cosine 2 pi is 1, and cosine 4 pi is also 1. So these 2 points already exist. So we have to look within the interval 0 and 2 pi. So the first thing that comes to mind will be for 2 pi over 3. This is because 2 pi over 3 is right here, and 4 pi over 3 is down here. So cosine 2 pi over 3 gives you negative 0.5, but cosine 4 pi over 3 gives you negative 0.5. And since they're equal to each other, that's a possible critical point. So we can say that 2 pi over 3 is a possible C value. And you can do the same thing for 4 pi over 3. So 4 pi over 3 would be like roughly over here. And you will get 8 pi over 3. 8 pi over 3 will go past 2 pi. But since the value is C is what we're considering here, so it can go past 2 pi. So we're going to subtract 6 pi over 3. And now we have 2 pi over 3. And as you saw earlier, 2 pi over 3 and 4 pi over 3 are the same thing. So another C value is 4 pi over 3. Because cosine 4 pi over 3 is currently on the bottom left of the unit circle. And that would be negative 0.5. And cosine 8 pi over 3 would go around one full revolution. So that's 6 pi over 3. And then pi over 3, and then another pi over 3, which is also negative 0.5. And since they equal, this is a valid C value. So the critical points are at 2 pi over 3 and at 4 pi over 3. So what I would recommend to do is take a visual approach to the graph, or like the function to what you need to find. So for example, imagine you have like cosine C is equal to cosine 2c. You would look for values on the unit circle such that if you have like an angle like this, if you were to multiply it by 2, it would be like over here, or over here, over here. So what I would do is just like take a graphical approach, or like visual approach, and look for what angles, when doubled, they have like the same value, or whatever's required in the problem. Okay, so now we're going to take the second derivative. So this would be negative sine x. This would be negative sine x, which turns it positive. So now we have sine 2x, but we have to take the derivative of the inside. So now we have negative sine x plus 2 sine 2x. And now we're going to plug in the C values to see whether it's a relative maximum or minimum or neither. So let's plug in the second derivative at 2 pi over 3. So that would be negative square root of 3 over 2 plus 2 sine 4 pi over 3. So this would be down here, it should be negative square root of 3 over 2. So which means that the second derivative at 2 pi over 3 would be negative square root of 3 over 2 minus square root of 3, which means that this is less than 0, which means that 2 pi over 3 is a relative maximum of the function. So now let's try the second derivative at 4 pi over 3. We're going to be down here again. So negative sine of negative square root of 3 over 2, which will be square root of 3 over 2, minus or plus, depending on what happens, sine 2x. So 2 sine 8 pi over 3. That would be up here, which means that sine is positive, which means that this will be plus square root of 3, which is greater than 0, which means that this value will be where a relative minimum occurs. So now we're going to find the maximum value and the relative minimum value. So it should be relative minimum and relative maximum. So this is 4 pi over 3. So 2 pi over 3 in sine x will be square root of 3 over 2. Subtract 1/2 sine 2x, or 4 pi over 3, will be negative square root of 3 over 2. So now we have square root of 3 over 2 plus square root of 3 over 4, or 2 square root of 3 over 4 plus square root of 3 over 4, which would be 3 square root of 3 over 4. So this is 3 square root of 3 over 4 for the relative maximum. And now for the minimum, we do the same thing, but we plug in 4 pi over 3. So f of 4 pi over 3 will be sine 4 pi over 3, and that's going to be negative square root of 3 over 2 minus 1/2 sine 8 pi over 3. So this is the same thing as sine 2 pi over 3, because you basically did one full revolution. You could subtract 6 pi over 3, because 6 pi over 3 is equal to 2 pi. And you would just go back to where you started. So now we have pi over 2, then pi over 2 over here. So now we have negative square root of 3 over 2 minus 1/2 multiplied by square root of 3 over 2. So we can multiply this by 2, and that's just 4. And now we have negative 2 square root of 3 over 4 minus square root of 3 over 4. And we have that this is negative 3 square root of 3 over 4. So it seems a bit messy, so I'm going to write it neater over here. Over 4. But now we have to check the endpoint extrema. So now we're going to plug in sine of 0, 0 minus 0. So we have 0, 0 as a point. And now let's try 2 pi. Sine 2 pi is also 0. Sine 4 pi is also 0. So we have 0, 0. But these are not relative minimum or maximum because they occur at the endpoints and there are no other values to compare to. So we know that the relative maximum occurs at the point 2 pi over 3, 3 square root of 3 over 4, and that the relative minimum occurs at 4 pi over 3, negative 3 square root of 3 over 4, and that is going to be our final answer. Okay, so now we're asked to find the graph of f of x and the second derivative of x based on the graph of f prime of x, or the first derivative. So what we're going to be looking for here is the extrema and the x-intercepts of this graph. So whenever a function has extrema, that means the function's derivative is equal to 0 at that point. So let's start with the second derivative of x. So f prime prime of x. So this is going to be equal to 0 whenever there's an extrema. So right here, the second derivative is equal to 0. Right here, the second derivative is equal to 0. And right here, the second derivative is also equal to 0. So let's say this is roughly 2. So we're going to draw an estimate of the graphs. So you don't have to make it exact. And it's going to be 0.5. And down here matches up with negative 1.5. And right here is going to be 0 because that's where the extrema occur. And now we're going to look around the extrema. So as we can see here, from the left of this extrema, the function is decreasing, which means that the second derivative is negative because the slope of the derivative is the second derivative. So the slope right here is negative, which means that the second derivative is going to be negative. But right here it starts increasing, which means that the slope is positive. We have to go back to negative. So now you start decreasing. So now you're negative again. But now you have to start increasing at 2. And that's how the function looks like. So another thing to look for is the degree of the graph. Since this polynomial is of degree 4, 1, 2, 3, 4 roots, that means that the original function is of degree 5 and that its derivative is of degree 3. Because each time you differentiate a polynomial, you subtract 1 from the degree. So if you have like f of x is equal to 5x to the power 5, well, its derivative will be 25x to the power 4. As you can see here, it has 1 less degree than its previous one. So using that knowledge, the derivative has a degree of 4, which means that its second derivative must have degree 3, which lines up here because it intersects the graph 1, 2, 3 times. So now let's draw f of x. So if you know leading coefficient behavior of a function, then you're able to determine the leading function behavior of its derivative and its antiderivative. So if you have a even degree function that is positive, then it would look like this. If you have an odd degree function that's positive, it would look like this. If you have a negative even degree function, then it would look like this. And if you have a negative odd degree function, it would look like this. So f prime of x is an even positive degree function, which means that it would be a positive, which means that f of x would be a positive odd degree function. And the same thing can be said for the derivative of f prime of x. As you can see here, it has the same behavior as this graph over here. So knowing that, the function f of x will behave like this one right here. So let's try plotting our extrema. So we're going to be looking for when the derivative is equal to 0, because that's where extrema occur. So at -2, there's an extrema. At 0, there's an extrema. At 1, there's an extrema. And at 3, there's an extrema. So let's look for values around it. So as you can see right here, the function is increasing because its derivative is positive, which means that its rate of change is positive. So the function will look like this. And then at 2, it starts decreasing. And then at 0, it starts increasing again. So that means there's a relative minimum right here and a relative maximum up here. And then at 1, you're increasing. And then you pass 1. So you can be like up here maybe. So at 1, you're still increasing, but then after you pass 1, you start decreasing. So there could be a relative minimum right here. And then at 3, you go from decreasing to increasing, which means that there's a relative minimum right there. And that's how the rough graph of f of x will look. So you have extrema, a relative maximum up here, relative minimum down here, relative maximum up here, and a relative minimum down here. And you would have 1, 2, 3, 4, 5 roots, which lines up with what was said earlier. And this is the final answer. So now this is our last problem for today, and we're going to sketch the graph of f of x and f prime of x based on the graph of f prime prime of x. So let's start with the first derivative, and knowing what we know, we're going to look for when it intersects the x-axis and its leading coefficient behavior. Since this is positive, that means f prime of x is going to look like this, and that f of x is going to look something like this. So this is degree 3, which means that f prime of x will be degree 4, and f of x will be just 5. So we're going to apply our extrema. So -1, -1. Let's say that's 0.5, and that this is roughly 2. So at -1, we go from decreasing to increasing, which means that there's a relative minimum right there. So let's say we go like this, and then we go right here, then we start increasing, and then at 0.5, we go from increasing to decreasing, so we look like this. And then at 2, you go from decreasing to increasing, which means we will have a relative minimum right here. So this is a relative minimum, relative maximum, and a relative minimum, and that matches the leading coefficient behavior said earlier. So now let's find f of x. So we're going to verify f of x using concavity and the first derivative. So we're going to look for values where the first derivative intersects the x-axis. So let's say it intersects right here at 0 and at 1 and at, let's say, -2. So the graph goes from increasing to decreasing at -2, so there's a relative maximum. So this goes increasing, then decreasing, then at 0, let's say like over here, at 0 goes from decreasing to increasing, which means there's a relative minimum. And then at 1, it goes from increasing to decreasing. And then lastly, at, let's say, 3, so this is like 3 roughly, it goes from decreasing to increasing. And as you can see here, it has 1, 2, 3, 4, 5 roots, which matches the degree stated earlier. And we can verify concavity by looking at the second derivative. So it says that it searches concavity at -1. So at -1, it goes from concave down to concave up. And then at 0.5, it goes from concave up to concave down. And then at 2, it goes from concave down to concave up, which matches what is shown here. And that is our final answer. Thank you for watching today's video. I hope you enjoyed, and stay tuned for more. Goodbye.